Welcome to the Boston Structural Heart course. We will be continuing with the Cardiac Anesthesia Fellowship Lecture Series today. In our last presentation, we discussed the basic physics of comprehensive intraoperative TE examination. Continuing on the same theme, we'll be discussing a little bit more detailed and practically applicable physical principles of color flow Doppler, Bernoulli's equation, and continuity equation, which we believe are essential knowledge for anyone who is performing a comprehensive intraoperative two-dimensional echocardiographic examination. Enjoy. All right, let's start with a comprehensive intraoperative 2D examination presentation 2. This will also relate to the workflow of examination, both protocol and conduct, but we'll be diving a little bit more into the practical physics of quantitative echocardiography. And for that, we'll be discussing Doppler, the principles of color flow Doppler, Bernoulli's equation, and continuity equation in this presentation. But before we go on, let's recap what we learned yesterday. If about an hour worth of presentation you remember only two diagrams, these are the ones that should be remembered. The two holy triangles of imaging. The triangle number 1 determines how much you want to see, that's the sector size, how fast you want to see, that's your predilection for temporal resolution, and how good you want to see, that's spatial resolution and line density. The holy triangle number 2 is based on how deep or how superficial you want to see, or a balanced image. When you want to optimize penetration, which means you want to see very deep into the tissues, you use a lower frequency or longer wavelength transducer, compromising somewhat on the resolution. And if you want to optimize resolution, or you want to see something superficial, then you use a higher frequency transducer with a shorter wavelength, and of course, you wouldn't be able to see structures deeper into the tissues. So the entire examination is set up to answer or to conform to these requirements, and every sonographer must try to establish what the imaging requirements are based on these two holy images of imaging triangles before they proceed any further. All right, let's move further to the next principle, and that's the Doppler principle. Like everything else, I would like to give you a slight historical perspective, and there's a little interesting historical trivia here. Johann Christian Doppler was an Austrian mathematician, very famous in the 19th century. Based on his experiments and observations, he described changes of light wavelengths in astronomical principles, that stars moving away or towards the Earth had different frequency of light, or wavelengths of light that were being seen with blue and red. And his famous paper on the colored light of double stars and other heavenly bodies was presented to the Austrian Scientific Society in mid-19th century. And what he analogized was that a ship moving out to sea would encounter waves more frequently than the ship returning to the shore. And we'll explain that with an example. This is as a matter of fact, one of the simplest examples to understand Doppler. Another Dutch mathematician named Buys Bellot, who was a harsh critic of Doppler theory and didn't believe anything like that would happen. So he tested it in 1844 by having musicians playing trumpets on a locomotive while it passed by the platform of a train station. And the observers on the platform observed that there was a significant change in the pitch of the approaching and departing locomotives, and they confirmed the Doppler principle. So this guy, despite being a harsh critic, inadvertently ended up proving and extending the application of Doppler principle from light to sound waves. So this is an animation made by one of our fellows, and you can see this. One of these ships is going towards the shore, and the other is going towards the open sea. And whereas the number of waves that are coming towards the ship are exactly the same, the frequency of the waves is exactly the same, but just because they're moving either away or towards the transducer, they tend to appreciate that there are a different number of waves coming through them. So whether the observer or the source moves towards each other, that changes the frequency in which you encounter those events. So that was a very nice animation made by one of our fellows, and makes this concept very clear. If you can look at it one more time, and that is two ships, one is moving towards and the other is moving away, would encounter the different number of waves. Now, whereas we'll discuss this Doppler in the physics and hemodynamics workshop in greater detail, What we are trying to discuss is Doppler shift, which means the difference in the sound wave that was transmitted and the sound wave that was reflected back from a moving target. So that's called the Doppler shift, the change in the frequency of the two of them. And we'll discuss this Doppler equation and formula in greater detail in the physics and hemodynamics workshop. But for now, you need to see that it is the Doppler shift is the difference in the frequency between the received and the transmitted frequency. And it is determined by this formula, which is 2, the transmitted frequency. This is the cosine angle of the angle of interrogation of motion. And lastly is c, that's the speed of sound. Now, the most important situation over here is this number 2. Now, this is a question that is often asked in the board exams also, what does this 2 represent? So what it represents is that in situation 1, when the sound is transmitted, the transducer acts as a transmitter and sends the pulse towards a moving target. Let's say that's an RBC. Now, when and as it strikes the target, that is a moving RBC, and it moves back towards the transducer. Now the RBC is acting as a transmitter, and the transducer will be acting as a receiver. So there are essentially 2 Doppler shifts: one when it is going towards the red blood cell, and one when it is coming back towards it. So that's the reason that it's in a single cycle of transmission and reflection. Actually, there are two Doppler shifts: one during transmission, when it is striking a moving target, and when it is reflecting back. Cosine angle, you tend to see the maximal Doppler shift when you are absolutely parallel to the direction of flow, and as you are moving away from the absolute parallel position, the value of cosine decreases below 1, and therefore your Doppler shift tends to decrease. So that's the formula. Remember it. But for those of you who will be attending the physics and hemodynamics workshop, this will be discussed in greater detail in that one. So the first kind of Doppler is a continuous wave Doppler, in which there are separate transmission and reception systems in a transducer. One crystal is continuously ringing and sending out the pulse, and the second one is continuously receiving all the reflected signals and establishing the highest Doppler shift, or the highest speed of the target is moving. So there's one element to transmit and one element to receive, essentially having a duty factor of about 100% or 1. So signals obtained from the region of overlap between the transmitted and the recovered signals have the highest sensitivity, and then that's where you get the maximal Doppler shift, and that's continuous wave Doppler. Now, as you can imagine, since you are continuously emitting and continuously receiving, there'll be an element of range ambiguity. You'll be able to get the highest velocity in the line of interrogation, but you'll have range and ambiguity in not knowing where exactly this Doppler shift is occurring, and therefore all that you receive is the highest velocity because you're receiving all signals that are coming back to you, and you're not time gated, and therefore you cannot really establish where exactly this Doppler shift is occurring. Now, if you look at the Doppler profile, it's like a velocity time integral envelope. It has a vertical axis demonstrates the Doppler shift, the horizontal axis demonstrates the time, the grayscale, which means how intense it is, represents the amplitude of the signals, or the number of RBCs that have been interrogated. Velocity is the peak velocity at a single location, of which we are not certain where exactly it is happening in this entire angle of interrogation. When it is above baseline, it is moving towards, and when it is below the baseline, then it is moving away from the transducer. So it's below, it's moving away from the transducer. So that's what the signal profile of a continuous wave Doppler looks like. So now what happens is, this is what is referred to as the demodulation of continuous wave Doppler. That is how this frequency is extracted. How do we exactly come to know that what the Doppler shift is? Imagine this is the reference signal. This is the one which is being transmitted to the from the ultrasound transducer to assess the velocity in the line of interrogation. It is called the reference signal. Now, the detected Doppler shifted signal, which means the one that is coming back, which is either of a higher frequency if the target is moving towards, or a lower frequency which is moving away from this one. Now, both these signals are multiplied. This is called signal multiplication or mixing to understand how much are they out of sync with each other, and that determines the Doppler shift. And later on, high frequency oscillations during the process of demodulation are removed, and what is left is the level of out of syncness with each other, out of synchronization with each other, and that is referred to Doppler shift, which means you have a reference signal, you have the detected signal. Both of them are mixed, and you find out by multiplying them where they are out of sync with each other. They're mixed and multiplied, and high frequency oscillations are removed, and what remains is a continuous wave Doppler signal. Now, this being a little complicated mathematics, but this is how you should remember it. But the most important thing regarding the continuous wave Doppler is that since one crystal is continuously emitting the sound and the other one is receiving, you do not have any aliasing, and you will detect whatever the highest velocity is. However, you have range ambiguity, which we do not know where exactly that sound is coming from. In contrast to that, what we have, the other thing, is referred to as the pulse wave Doppler. If you look at, this is the deep transgastric window, this is the aortic valve, and you're not interested in knowing exactly what the whole velocity is throughout the course of this left ventricle. All you want to know sometimes is the velocity in the left ventricular outflow tract. And therefore, you can identify a location within the line of interrogation where you want to know the exact velocity. You do not want to, you're going to be ignoring all the signals coming from this place or this place. All you want to know is the velocity at this point, and this is called pulse wave sample volume, which means you want to identify the size and the location of the region where you want to see whether the RBCs are headed towards you or headed away from you. And the technology that we use for that one is referred to as pulse wave Doppler. So this is the transducer. This is the depth to which we decide to measure or identify the flow, whether it's going away or towards this one. And that size of that sample volume is determined, and the depth is determined by the operator. However, as you can see that as the beam widens, since it travels away from the transducer, as you will put this sample volume further away from the transducer, it will automatically enlarge in size, and you will be interrogating a larger area. The flow profile that we get for pulse wave Doppler, unlike the continuous wave Doppler, is hollow from inside, which means it is not really detecting any velocities along the way. It is only detecting velocity at a specific location, and therefore range ambiguity is not the issue here. You identify precisely where the Doppler shift maximally is occurring, but there's a certain price to pay for that, and that price is called the likelihood of aliasing, and we'll get to that in a second, and how pulse wave Doppler is susceptible to aliasing. But to recap, the depth of the sample volume, the location, and its width and its length is determined by the operator to know exactly how much of an area needs to be interrogated for ascertaining whether the flow is coming towards or away from the transducer. So depth is achieved by electronic gating, which means you will know, for example, if hypothetically speaking, if we were to know the speed or Doppler shift or the direction of flow 1540 meters from the transducer, then we would send out the pulses, but we will only analyze the pulses that will take 2 seconds to come back, because the speed of sound is 1540 meters per second. By putting the sample volume at 1540 meters, we have established, or we have time gated our pulse wave Doppler by saying that whereas reflection will be starting to happen all through this course of this transmission and reflection, but all other reflections will be ignored other than the one that are taking 2 seconds to come back, and that's called time gating. So scattered signals are detected by the same transducer, because now you are sending out a signal, waiting, and then there's a go-return time involved in assessment of velocity, and therefore there is the likelihood of aliasing, which means if the object of interest or the location of the sample volume, the RBCs are moving faster than you can analyze them, then you wouldn't be able to tell whether they're moving away or towards the transducer, and that's called aliasing, and that's the reason we cannot use pulse wave Doppler at certain locations, because the velocity or the RBCs is way more than what we can detect. The rest of the process of amplification and demodulation is pretty much the same, but this time it's all happening not for the entire line of interrogation, but only for the at a location of the sample volume. So only those echoes are detected in a narrow time interval after pulse which correspond to a certain depth. All others are rejected. That's the most important point. And that depth is determined by the operator, and the ultrasound knows how long it'll take for the signals from this depth to come back. Other than those signals, everything else is rejected. So for pulse wave Doppler, if you want to remember any diagram, this is the one that you should remember. And that kind of tells you what the story is. So this is the reference signal like we send it out in continuous wave Doppler. However, the received signal is only coming after certain times. While they're coming immediately, as soon as it starts transmission, reflections start to come back. But we are interested only the ones that are coming from the sample volume. And how we know that the location of how we know which ones to discuss or to analyze are the ones which are taking a certain specific time based on the depth of this one. So this is the reflected signals, and we are receiving time-gated pulses that from the sample volume. Now these time-gated pulses are again multiplied with the reference signals at those specific locations to get a multiplied signal. And then again, by taking out the high frequency oscillations, we removed by the low pass filter and what we know is the Doppler shift. The most important thing is that we have to be able to analyze accurately the pulses coming back from that location, because if the go return time is too long, and by the time the second pulse goes to analyze the same RBC that has moved out of the sample volume, we would not know exactly which direction the RBCs are going, because then you will misinterpret and interrogate another RBC in the next cycle that may be closer or farther away from you, and therefore you'd be getting aliasing at that time. So the problem with the pulse wave Doppler is in the process of signal processing, and that is it is time gated and therefore susceptible to aliasing. So this is the only pulses coming from a certain specific location of the sample volume are analyzed, and the rest are ignored. And this is called, demodulation we call phasing, and you can see the demodulated and amplified signal. It is completely in sync and it's completely positive. It is slightly out of sync, it is slightly negative, it is even more negative, even more out of sync, and this one is completely in the opposite direction, and therefore it is completely out of phase and peak negative amplitude. And this would be not having no Doppler shift. This is progressively positive and then going away from the transducer since they are completely out of sync. So this process is called phasing. However, not going into the greater detail, for echo only pulse wave Doppler, you can detect the velocity at a specific location and it is susceptible to aliasing, unlike continuous wave Doppler. Now this is another diagram that you should remember, and that's the high pass filter, which means clutter signals originating from tissues and stationary objects, and low amplitude and high frequency signals are the ones that remain over here. So this is a very high frequency signal, see from 5 to about 4.99 to over 5 megahertz. This is the clutter signal, which is low frequency and high amplitude. In the process of demodulation, high frequency signal is removed and what remains is the low frequency signal, and high amplitude signals are left behind. In the process of demodulation removes the high frequency signals from tissues, and Doppler shifted signals and clutter signals from tissue are left behind. And then you finally have the high pass filter, which removes the high amplitude clutter signal, and very low velocity signals are the ones that are, and low frequency signals are what remain, that is the blood signal. So original signal is received as clutter and meaningful signal. The process of demodulation removes the high frequency signal, and high pass filter removes the high amplitude signals in the last phase to what remains as the Doppler signal. Complicated physics, but based on what controls you see on the machine, these are important things to know. So that brings us to color flow Doppler. Now this is a little bit more complicated, and we will get into a little bit more detail of what a color flow Doppler signal is. First and foremost, color flow Doppler signal is a pulse wave Doppler signal, because obviously you are locating at a certain specific, the flow location is a certain specific point in the field of view. As opposed to a pulse wave sample volume at a precise location, we have multiple pulse wave volumes over a region where we put the entire color flow box. And we want to know the Doppler shift or the motion of all those signals either away or towards the transducer. If you look at a pulse wave signal, a color flow signal, you can see this is the frame rate, this is the depth, these are the 2D parameters, which means the gain is 68%, the compression is 50, the persistence is off, and you're in the harmonics penetration mode, which means you want to see further into the tissues. Now this states the color flow parameters, which means your gain of color flow gain, which is the analogous to the two-dimensional gain, is 59%. Your frequency range is about 3.3 megahertz based on this penetration, because you're looking at whoever the sonographer was wanting to see deeper structures. You have set your Wall filters, which is the one we just talked about, demodulation and high pass filters, to very high, which means the high amplitude signals will be taken out, and your sensitivity is very low. This demonstrates the grayscale, and this demonstrates the BART scale, which we will talk about in a second. And this is your upper limit of flow, which is 0.7 meters per second in the direction of the transducer, and this is 7 meters per second, 0.7 meters per second away from this is the upper limit of velocity that you can detect. And this is, of course, the output power. Now you can take a look at these two controls that we've changed to demonstrate the impact on color flow signal. The one on the left is a low Nyquist limit, everything else being equal. You can see that the upper limit of velocity either towards or away from the transducer has been reduced to about 0.3 meters per second, and that is leading to a lot of the turbulence being seen over here, which we otherwise wouldn't have been able to detect. So that's lowering the Nyquist limit, which means you tend to see the lowest velocities, and you're unlikely to appreciate higher velocities than that, and more than a higher velocity than 0.3 meters per second will be seen as turbulence or aliasing, which will be ambiguity in the total direction and speed. The one on the right here, as you can see, has an excessive gain, which means the gain has been increased from 48% to about 74%, and that is leading to not that there's not much of the velocity upper limit is 0.5 meters per second in either direction, but there's excessive gain. This is analogous to 2D gain when you increase the sensitivity and amplitude of all the returning signals. And the difference between lower Nyquist limit and excessive gain is that in excessive gain, what we are seeing is called a bleed over, in which the color flow signal is beginning to overlay the grayscale signal. That's how you differentiate something between low Nyquist limit and excessive gain. Despite being low Nyquist limit, the boundaries between flow and no flow and flow and tissue are very easily appreciated, whereas the ones over here cannot be seen as well. So that's one of the changes in the control that you can take a look and see this thing. Now let's get to the BART scale, which is called blue away and red towards. So the normal range is maximal Doppler shift in the direction towards the transducer. This is the maximal Doppler shift away from the transducer. This blackness in the middle does not represent that there's no flow. It represents that there's zero Doppler shift. The flow could be completely orthogonal at this location, and you wouldn't be able to know. So this is zero Doppler shift. And this is the peak Doppler shift towards and peak Doppler shift away. So BART system is blue away, red towards. We can also have the variance map, which I tried to draw with some gradient in this in this flow velocity map, which means this is this is one of those maps that are default to certain systems and can be changed when you change the BART scale to appreciate some side-to-side motion also. This variance map is important, particularly in locations where there's possibility of having side-to-side flow, mostly in the left ventricular and the right ventricular outflow tract. But more or less, majority of the systems, majority of the time, all you need to know is the BART, that is blue away and red towards system, to appreciate what it is. Now let's go over the anatomy of a color box. Now this is a little bit more complicated discussion. Let's just say this is the color flow box that has been placed on the mitral valve to analyze the flow convergence or for the mitral regurgitation. And this box consists of multiple lines. And you look at, even go close to the lines, they are closely spaced, but you zoom on them, and each line has a certain width, And if you look at even more closely at each line, what it looks like is this thing. And if you zoom on it a little bit more, each line has multiple boxes in it, and these are known as color packets. And if you look at closely each one of these boxes, it looks like this. So zooming from a color box to the lines, to multiple lines, then single line, and then you zoom on to the line and you will see this color packet in each of these boxes, and this is called a color packet. And this entire color box consists of hundreds of these color packets that have been placed all over the place in this region. We'll try to explain that with this animation, which we are very proud of. This is analogous to Google Earth. We are zooming on to a color box and looking at this box, that when you totally go into this color box, this is something that it looks like. Now we'll go over this animation over some time, and then we will see what it means. So imagine that this is the transducer, this is an RBC-A, and this is an RBC-B, and this is an RBC-C. RBC-A is going from this location to this location, and RBC-B is coming from this location to this location. Now, the go return time for RBC-A at this time is this much. And it moves to location 2, the go return time for RBC-A becomes longer. Now, the go return time initially is longer for A in this instant. The initial go return time for RBC-B is this much, but when it moves from location 1 to 2, this is what the go return time is, and this is go return time for RBC-B is shorter. Now, the difference in time between these two locations, the delta time from location 1 to location 2 and location 1 to 2 for RBC-A and B, is analogous to proportional to the distance the reflector has moved. The time it takes for them to travel from one location to the other is proportional to the distance they have traveled, and that essentially is the Doppler shift, And this is how it is calculated. So for this RBC, it's not moving anywhere. So in total, it doesn't move anywhere, so there's no pulse 1 cancels pulse 2. For this one, we are able to appreciate whether both pulses that are sent towards this RBC demonstrate to be a shorter time or a longer time between the first and the second pulse. Obviously, between the first and the second pulse, we have a shorter time. For this RBC, we have for this one we have a longer time, and for this RBC we have a shorter time. If this RBC is not moving anywhere, so both pulses are the same, they cancel out. We demonstrate that there is no flow. So impulse 1 and impulse 2 are pulse pairs. So within a color box, color packet, pulse pairs are sent out for each RBC to demonstrate which direction that RBC is moving, and multiple pulse pair transmitted along a scan line to see it is analyzed by a pulse pair every now and then to demonstrate at each location whether it is moving away or towards this one. And therefore average velocity is gained for the whole region, whether all these pulse pair demonstrates all these RBCs go return time being shorter or being longer, and therefore that comes as a pulse wave Doppler on either towards or away from you. As you can imagine, if the RBCs are moving faster and in more chaotic pattern than the two pulse pairs can interrogate, then we wouldn't be able to know which direction and what speed these RBCs are moving. And that is the principle of color shift, and that is happening in each color packet. Multiple pulse pairs are being sent out to see the location of RBCs from one instant to another. Nyquist limit is the peak velocity that can be detected in any direction. And if you go beyond the Nyquist limit, that is referred to as aliasing, which is defined as ambiguity in speed and direction. Now that brings us to the last part of this physics, and that is the Bernoulli equation and the continuity equation. We'll start with the modified Bernoulli equation. Sorry about that, but the modified Bernoulli equation. So what Bernoulli equation is supposed to tell us is the consequences of stenosis. And that's what the entire Doppler, color flow Doppler echocardiography is all about. And that is the ability to interrogate and analyze the consequences of stenosis. As a result of stenosis in a vessel or in a wall, what happens is that there's not only change in direction, there's change in velocity, there's change in pressure, there's change in pulsatility, and lastly, the laminarity. And that's what we are supposed to detect with modified Bernoulli equation. A lot of people ask me in relation to Bernoulli equation, what is a gradient? It's not an absolute number. It is the change in value or quantity of a certain specific numerical that you want to know, which means it is higher here, it is lower here. The gradient is the difference between this position and this position is referred to as the gradient. It's not an absolute number, but difference between two of them. With continuous wave Doppler, what we have read so far, it tells you the peak velocity at a certain location, or the peak gradient of where exactly that gradient is happening. Pulse wave Doppler, on the other hand, it tells us the gradient at a specific location, and we'll get to that in a second, what the gradient is. But I just wanted to demonstrate the difference between pulse wave Doppler gradient and continuous wave Doppler gradient. We also have the mean gradient, which means the difference, average difference over a certain time frame, or the peak gradient that is happening at any specific moment in time. So let's get to it. So the principle of a Bernoulli equation is based on the principle of conservation of energy, which means the total energy of a system remains constant. As you can see, let's assume that this is aortic stenosis. Proximal to aortic stenosis, there is a very high pressure built up because of obviously obstruction, and the velocity is very low. And you can imagine this would be a very high potential energy and very low kinetic energy, which is proximal to the stenosis before the stenotic valve. So as the blood gushes out of this stenotic vessel, there's a very high velocity. The blood gains a lot of velocity. Now this is practically simultaneous increase in velocity and a decrease in pressure because of the law of conservation. And this is the pent-up potential energy here is being converted to kinetic energy. So there's a drop in pressure. So gradient essentially is the difference in the pressure proximal to stenosis and the drop in pressure distal to the stenosis. So this is the pressure-velocity relationship. Proximal to stenosis, the velocity is very low, pressure is very high. As you go to the stenosis, velocity increases and pressure tends to decrease. So if you understand that, that's step one, and that is the total energy of a system remains constant. Proximal to the stenosis, there's high pressure, low velocity. Distal to the stenosis, there's high velocity and low pressure. So let's get to the Bernoulli equation over here, and that is based on this principle that the total energy of a system remains constant, and velocity and pressure gradient, the more higher the increase in velocity after the stenosis, higher will be the gradient. That is the difference between the proximal and the distal pressure. So this is a complicated equation that demonstrates the pressure difference, the proximal velocity, that's V1, V2, the velocity at narrowing. This is the density. This is dV or dt is the change in velocity over time. This is the distance over which the pressure decreases, and the viscous resistance, and then finally viscosity. It's a complicated equation. We will try to simplify it in a second. So let's put this equation here. Now you can see that flow acceleration can be ignored because it is zero at maximum. So the flow acceleration can be ignored because at maximum velocity, that's what we are trying to measure, it is zero. So we can ignore that. Second is viscous friction is negligible, and in the middle of the vessel, that's where we are measuring. So viscous friction can also be completely ignored. Then 1/2 mass density of the red blood cells is 4. So we substitute 1/2 P with 4. Plus the proximal velocity is very low, and particularly if it's low, less than 1.5 meters per second, it can be ignored, and therefore we can remove the V1 from this equation. And what is left behind is delta P is 4V squared, which means the drop in pressure, or the pressure gradient between proximal to stenosis and distal to stenosis, is 4 times the square of the peak velocity. So that's the modified Bernoulli equation. And if you understand this principle, trust me, you understand almost half of echocardiography. So now apply this to this one. So higher pressure proximally, low velocity, high velocity, low pressure, and the difference between P1 and P2 is 4 times the square of this peak velocity. So that is called Bernoulli's equation. Now, if you think of it, I'll make it a little bit more complicated. As the velocity immediately distal to the aorta is the maximum drop in pressure and the highest velocity, But as we will go away from the aorta, the velocity will gradually decrease because you'll have the maximum momentum here, will gradually decrease. So if you were to measure the pressure difference between the proximal to stenosis and the ascending aorta, that would be a little less because this is where the maximum velocity or the maximal drop in pressure is. So this distal phenomena, that is increase in pressure and the decrease in gradient between P1 and P3, is referred to as pressure recovery. We'll discuss this in a little bit more detail, and you will tend to find out that this actually makes a lot of sense. So as you can see here, this is the LVOT in a stenotic aortic valve situation. We have a very high proximal pressure, a very low velocity. Location 2 is immediately distal to the aortic valve. When as the blood gushes out of the aortic valve, there's a simultaneous increase in velocity while there's decrease in pressure. The continuous wave Doppler will measure the gradient between location 1 and location 2 as the highest pressure difference between this location and this location. However, as the blood goes away from the aortic valve into the ascending aorta, the velocity gradually decreases. And if you were to have a catheter in location 3, that's what we have in cardiac catheterization, and you try to measure the pressure difference between the LVOT and the ascending aorta, you will have a lower pressure difference between these 2 points because there has been a phenomenon of pressure recovery, that is, the velocity has reduced and the pressure has increased. So that's referred to as pressure recovery. Keep that in mind when we go on to discuss some aortic stenosis scenarios. So applying the modified Bernoulli's equation here, you can see the peak gradient is the peak velocity. We multiply that with 4 and square the velocity, and that would be the peak gradient, that the difference between the proximal and distal pressure. However, if you were to trace this velocity time integral, you often see in those machines those small little dots that go along with the edge of the velocity time integral. So each of those dots is actually a computer performing a 4v square, and as it performs from the minimum pressure to the maximum pressure, it is kind of averaging out the entire pressure over the duration of that ejection or regurgitation phase. So if you look at the lower end of this slide, you can see that calculations based on the peak gradients. If you have 2 meters, that would be 16 millimeters. For a peak velocity of 3, 4v square would be 36. 4 times 4 square would be 64. 158 millimeters of mercury, and then finally 39.6. These are all derivatives of 4v square that's based on the peak velocity and then conversion into a pressure gradient. Lastly, we come to the continuity equation, which is the second 50% of quantitative Doppler echocardiography, and that is based on continuity of flow, which means the flow between 2 contiguous points is equal as long as there's no shunt between them. When we are measuring the continuity equation in human tissues and human bodies, human body and intracardiac flows specifically, the assumptions are that the flow is laminar, it's not turbulent, it's a non-expansile conduit, there's absence of any shunt. We are since using pulse wave Doppler to identify a velocity at a certain specific location, that the LVOT is the area that we measure the pulse wave velocity, so they have to be measured exactly at the same location. And of course, you have an absolute parallel alignment of the Doppler. When we get to 3D, there are certain other assumptions also, but for the sake of simplicity, I will kind of keep them a little short now. So this is based on the concept of stroke distance, which means if you know the area at a certain location, and you know that the distance that area has traveled over time, you can get a volumetric derivation from that. And if you can look at this one, we know the area at this specific location, and if this area travels this much distance in a certain tube, then we can get a volumetric derivation and know the stroke volume at a certain specific location. And the same principle is applied to cross-sectional area of the LVOT. We put a pulse wave Doppler sample in the LVOT and derived a volume velocity time integral. The area under the curve represents the total distance or the flow that has happened over time, and we can multiply the stroke volume with the heart rate to derive the cardiac output at any given moment in time. So this is purely an extension of the principles of area in a tubular structure traveling a distance over time, represented by the velocity time integral, giving a stroke volume at that specific moment in time. So if you take a look at it one more time to reiterate, this is the area traveling a certain time in a tubular structure. Knowing this area and the distance to travel would give a volumetric derivation, and that would be considered the stroke volume and stroke distance. So now extrapolating this continuity equation, that is the flow at any given moment location is equal to flow at a contiguous location in the absence of a shunt, which means flow at location A, that is cross-sectional area of tube A, times the velocity time integral, that is a stroke volume at A, should be equal to stroke volume at B, that is cross-sectional area of B times the velocity time integral at B. And in the absence of shunt, that should be equal to the stroke volume at C, which is derived by cross-sectional area of the tube at C and the stroke distance at time C. Now, A stroke volume should be equal to B, should be equal to C. Now, we can extrapolate and simplify this thing for two locations, more importantly for cross-sectional area of the LVOT and cross-sectional area of the aortic valve, VTI of the LVOT and VTI of the aortic valve. So knowing the cross-sectional area of the LVOT, knowing the cross-sectional, the velocity time integral of the LVOT and the velocity time integral of the aortic valve, we can solve this equation for the cross-sectional area of the aortic valve, which means stroke volume in LVOT should be equal to stroke volume at the aortic valve. And if you know the velocity time integral at the aortic valve, we can solve this equation for cross-sectional area of the aortic valve. Now, this brings us to finally the principles of continuity equation for aortic valve area calculation. The LVOT diameter is measured in the mid-esophageal long axis view. We'll go into further detail when we get to the actual image acquisition and quantitative echocardiography. This cross-sectional diameter is converted into radius by halving it, and then goes through the equation of pi r square. And quite intuitively, this is the greatest source of error because we are having the radius and then deriving a square root of it. So this can introduce a lot of error if you miscalculate the LVOT diameter. So this is all done in the mid-esophageal long axis view. The pulse wave Doppler is placed in the LVOT in the deep transgastric window to get the VTI and the stroke volume in the LVOT. Now the aortic valve, the VTI or the velocity time integral, is achieved with continuous wave Doppler in the same view, assuming that the highest velocities of the aortic valve, and then we solve that equation for stroke volume for cross-sectional area in the LVOT, for stroke volume in the LVOT to derive the aortic valve area based on continuity equation. The applications of continuity equation are in calculation of cardiac output and aortic valve area. That's the lion's share of use of continuity equation during clinical echocardiography. We can also use that for mitral valve area calculation, regurgitant fraction and volume by measuring the stroke volume at two locations and knowing the difference and the percentage fraction between them. And finally, for shunt fraction and shunt volume calculation in patients who have congenital intracardiac shunt, so we can know the significance of the shunt going from right to left or left to right side. So this concludes the second portion of the protocol and workflow of the intraoperative echocardiography. So we concluded on the physics section by discussing in greater detail Doppler, pulse wave Doppler, modified Bernoulli's equation and continuity equation. And these calculations and these physical principles form the basis of intraoperative TE examination, that is the quantitative aspects of it that we perform during image acquisition. Now we'll further discuss in the third and the fourth part the instrumentation, the setup of the instrumentations, the care and insertion of the TE probe, and finally the image acquisition and interpretation of comprehensive two-dimensional intraoperative TE examination. Enjoy and stay tuned. Thank you.